Now that we've derived the integrated forms of the rate laws, it's time to see what those are useful for. Here's a problem that's different from all of our rate law problems before. Now our data tables don't have initial concentrations and rates. Now these tables have time and a concentration. So we can use our knowledge of the integrated forms of the rate law to see if we have a zero order, a first order, or a second order equation. If our reaction is first order, we should see a similar decrease in the concentration for similar amounts of time passing by. This question is kind of tricky because we don't have the same amount of time passing in each step. Check out here. In the beginning, we change by 120 seconds, then 180, then 300, then 600. Fortunately for us, so we don't have to use a computer, the problem levels out and starts jumping by 600 each time. These are the pieces of data that I'm going to focus on because we have a consistent time difference. That's really important when you're tackling these questions. Keep the time difference consistent. So what we're going to do is we're going to subtract between 0.37 and 0.22, and that difference right there is 0.15. Then we'll subtract between 0.22 and 0.13, and we'll see that this is not the same numbers we had before. It's 0.09. And just to double check that I'm not crazy, I'll do one more set, and I'll see that the difference between 0.13 and 0.082 will be 0.048. Now these numbers are not consistent, which indicates to me that my line is going to be a little bit curved and not a straight line. So this is not zero order. In other words, the rate of the reaction does depend on the species present, like how much of it is there. So what we're going to do now is we're going to take the natural log of some of the more interesting data, the 0.37, the 0.22, the 0.13, and the 0.082, and see if the natural log of these numbers produces a linear slope. Okay, so I'm just going to draw a box here and input the data really quick. And we can see here in this new chunk of natural log of our concentration data that the change between our lines is all about 0.5 for each one of these pieces. We have 0.516, 0.53, and 0.46. In fact, if these were just rounded a little bit differently, you would see that there's 0.5 for each part. However, just to be thorough, I want to also check the 1 over the concentration data to make sure that that is not going to be a second order equation. After taking the 1 over concentration of each of our interesting data pieces, we can also see that the change between these sets of data is not consistent. In the first chunk, we have a 1.85 difference, then we have a 3.14 difference, and then we have a 4.5 difference. These are clearly not linear, which means our data best fits the situation where we have a first order equation. This helps us answer the first two chunks of our actual question, which are determine the rate law and the integrated rate law. For this, since it's first order, we can write rate equals K, hydrogen peroxide concentration in molarity. You can also write the rate the way that they have in the stem of the question, where you can write the differentiated form, negative change of concentration, change of time equals K concentration. On the AP exam, you could derive the integrated rate law if you want to, but it's not necessary. You can just derive it or use the one that's on the equation sheet. The first order rate law integrated form starts with the natural log of the concentration at a particular time. This will be your y value, with a negative kT for that slope part, plus the natural log of the initial hydrogen peroxide concentration. Luckily for us later, we'll see that the original concentration is 1 molar, which is going to make our calculations easier. For the next two questions, we're going to need to use the integrated form of the rate law to solve the question. Let's focus on this part, the value of the rate constant first. To solve for the rate constant, we just need to plug in any set of data that's not at the initial time to find the K. So what we're going to do is I'm going to choose the second line of data where we have time at 120 seconds and the concentration of the hydrogen peroxide at 0.91. So I'm going to put in the natural log of 0.91 equal to the negative mystery K times time, which is just 120 seconds, which is going to mean my K is going to have units of 1/seconds. That's pretty important on the AP exam to keep careful track of your units. Times the natural log of my initial concentration, which is 1, which is amazing. That means that my natural log of 1 is going to go away. That is a 0 automatically. Now I'll just use my calculator to calculate what the natural log of 0.91 is. That'll be negative 0.094311. Just keeping some extra digits until the end, and then I'll round. Equals negative K times 120. Divide that sucker over, and then we'll see that the rate constant for this case is equal to about 7.9 times 10 to the negative 4. 1/seconds. The last question in this problem is asking us to calculate the concentration of the hydrogen peroxide at 4,000 seconds, which we can now do because we know the rate constant. So we will plug and chug. We'll use our integrated rate law again and say the natural log of our mystery concentration at time 4,000 seconds is equal to the negative of 7.9 times 10 to the negative 4 times 4,000 seconds plus the natural log of 0, which cancels out. Now we'll just do a little bit of calculations. We'll see that these two numbers multiplied together equal about negative 3.14. Hey, that's kind of fun. It's pi. And then we'll see that we end up with this weird situation. We're going to have to undo a log here, which requires us to remember that to get rid of a natural log, you have to use the e function. That will cancel out this log. So in our calculators, please make sure that you push your e to the x button and then put in your negative, which is usually one of the buttons with the parentheses around it, 3.14. And then you should get that the concentration of the hydrogen peroxide at 4,000 seconds is equal to 0.043 molarity. Now it's really important for these kinds of questions that you make sure your answers make sense. If your concentration at 4,000 seconds is bigger than your initial concentration, or it's bigger than the concentration at 3,000 seconds, that's not going to make any sense because the reaction should have continued. So double check that your answers make sense, and then you're set.